Welcome to the Valve Studio. I am still on my little detour on my journey to ToneHenge this week. Actually, for the last couple of weeks. I think last video was a couple of weeks ago, and I'll go ahead and tell you about the progress I've made. I got my screen capture going on my Windows 10 machine. I've also got my webcam pointing down at my progress, and I'll go ahead and go over what I'm talking about. So the first thing is I'm going to go to the schematic. Now this is using this. I'm going to run Gerbil on this PSaw board here. This is a PSaw 5LP from Cypress, and you can get these for about $10. And they have far superior performance to straight Arduinos. And I'm going to be able to add in a bunch of extra stuff. If you're interested in what I'm doing on that side, just watch the last video, or I'll kind of talk about this a lot more. But here, I'll just give you a brief overview of what we're going to talk about. So here's our schematic. Here's the basically my controller, and I've added a bunch of connectors onto it so I can connect up all the stepper motors. I'm using the integrated step servo motors, so I have to just run my direction and pulse pins out to those. And then I also have I'm making this as a standalone CNC machine that's capable of doing manual operation. So I need to be able to control Gerbil from on the internal microprocessor. This microprocessor here is running at probably around 80 megahertz, and it can easily do Gerbil and a bunch of other stuff. But I just kind of go over a few things here. I'm going to be able to do infrared remotes, so I can use one of these DirecTV remote controls to be my pendant. And here's the IR receiver on the schematic. I'm using a little Wemos D1 Mini here for my Wi-Fi connection. And I've got this configured up so that I have a file system on the flash of a 3 megabyte file system, so I can put my G-code over there if I wanted to. I'm also got an SD card reader, which is, well, not around, but it's an SD card. I'm going to be able to read in the SD card based Gerbil files or G-code files and actually be able to stream those into Gerbil. And lastly, it's all pretty complicated what I'm doing. It's way beyond just a simple project. I have a couple of these I/O expanders in here. These are microchip 2317s. 23017s are 16 bits of I and O, and each one of these individual bits can be an input or an output. And I got those connected to switches, so I have 8 input switches on one of these channels, and then I have a bunch of outputs, and I'm running LEDs. So I'll go ahead and show you that in a minute. I got the boards made over here, and I was really impressed with the quality. I got these made over at JCL PCB. I submitted my design on a Monday evening, and a week later, on Tuesday morning, DHL showed up and delivered these. So these are my raw boards. I apologize for the lighting. These boards are highly polished so that they're very reflective. I've been doing PC boards like this for probably 20 years. And yes, it's true. I did get 10 of these. If you look down here on their website, I did 2 layers, 10 of these with 100 by 100 millimeters for $2. And the shipping DHL to Colorado was about $18. So I got 10 of these boards for $20, which is awesome. You can't really see it on my silly little webcam here, but the registration of when you look at these inexpensive PC boards, what you want to look for is the registration of the drill holes to the center of the pads, and it's excellent. This is just excellent work. And the silkscreen registration to the rest of the features on the board, as well as the how how well defined the solder mask is. And I gotta say, for me to get 10 boards for $20, you can't beat that. There's no reason why you'd ever want to make your own boards at home. Not when I got them in a week. The capabilities this board has, I mean, in terms of size, you can go down to 5mm traces, which is 5mm traces widths and 5mm trace spacing, which allows you to do super fine surface mount work. All right, well, I'm in love with this little board, and what I've been showing you back here is one of the boards that I actually hand soldered all the components on. So I have all the connectors, and I have all the I/O pin expansion on here, and over on the other side, we'll flip over in a minute, but I have the switches and I have the IR detector. And down here I'm using a, if you look at the schematic, that particular part is, where is that on this thing? Oh, it's down here. I'm using a 3-pin voltage regulator, because I'm going to run my board, my machine, my open built machine at 36 volts. So I needed a way to go down to +5. Those PSaw boards run at +5. And you could use a regular 7805 for this. Well, not really, because some of the 7805 maximum input voltage is about 28 volts. But I'm using switching power supply with the same footprint down here. And this, I got these on DHCP for maybe $5. And this will be a 1.2 amps at with close to 31 volts across it. And it's super quiet, and I'm able to put some capacitance in there as well as some stuff. All right, so for those of you who have never done this with Cypress parts, you end up using their tool called PSaw Creator. I'm going to go ahead and load in some of these projects I came up with. So the first project, well, if we look at the main project, is the controller code from Bart Dring, and he's the one that ported Gerbil over to PSaw 5, and his project is broken up into a bunch of different pages where he has the communications. This is all the digital part of the design. Remember that PSaw has got digital fabric as well as analog fabric in it. So I took this design and I ended up adding in all the extra stuff that I wanted to do, and I figured out the pinouts, and basically using every pin on the processor to its fullest extent, let's just say. And then I did the board layout, and so that's where we are right now. But I'll show you some of these. I call them, in my development world that I control here, I do these things called baby steps. Baby steps are little sub-projects that allow me to check out hardware and be as simple as I can get. So these are the individual components of my project. So we'll start out with the LCD 2004 project, which, remember, I'm going to show you. I don't know if I'll be able to get this all on the screen, but here's like a mock-up of my control panel, and I have my jog wheel here, which has a quadrature output on it, and then all the buttons are going to fit through here. And then I have a room up here for my LCD display, which is a 20 character wide by 4 character high, and that is now I've done it. That is this display down here. This one up here is the one that's going to ride along top of right next to the spindle. And this one is a graphic display that you actually program up, and then I don't have to write massive amounts of data out to this. I can just basically write an update command. And this is one of those Nextian displays. And you can do the layout with their layout tool basically and create pages, so to speak, and then I can just say update this element on the page, and then this will render it. Because it's graphical display, I can have very large numbers on here, and we'll kind of show you that in a minute. Because that's one of the other sub projects, was to do the displays. But this one here is just doing this 20 by 40. This is the I2C device, and this guy on the back has got one of these backpacks on the back. Now, unfortunately, this backpack is not a dedicated LCD controller, which is kind of unfortunate. It is another one of these I/O expander pins thing from I think it's Philips, and so basically you have to control all the, there's about 8 lines on the back of this to actually control the rights to it. So there's actually a lot of I2C traffic, but I was able to kick the I2C up to 400 kilohertz, and I can do my complete screen refreshes in about a millisecond. So I'm not really bogging down my main processor by sending out a bunch of update commands to this. This one is a serial connection that I can run up to 115/200 kilobits, and so I'm able to send out my probably, I don't know, 25 characters to update the screen with all the status that I want to do over here. And there's a UART in here that I can set the FIFO width on, and so I won't really bog down the processor by sending commands to this one either. So I got the project open over here. That is my my baby step code to just run this display, and we'll go ahead and show you that. So over here, I just really basically run. See if I can zoom in here. There we go. All I really have on here is an I2C controller, and then in the software I just turn it on and write a bunch of stuff to it. So we'll go ahead and run this on the board now. Actually, I've got to plug this in. This is probably where I'll fail and bump the camera or something. Nope, I'm certainly bumping my rulers. I had a lot of problems this evening to getting this webcam set up correctly so you could see stuff, but hopefully this is going to work. Alright, so what I got loaded in here now is I know that this board has actually got this baby step project going, not that one. That one, talk about that one in a minute. This one is just running the I2C controller, and I'm doing updates probably about 5 times a second. And so if you look at this kind of closely, let me get a little pointer over here. Hold on a minute. Get my pointer out. Alright, so I got X, Y, and Z here. This is my coordinate system. I'm in G54. I'm in running mode. Now this is just all mocked up data. Come over here to kind of plot out how, what kind of resolution I want over here, and what I'm able to display over here in this region. So here are the active G codes. So G1 is not absolute. This one is feed dependent. 21 is, I think that's millimeters, and 90 is absolute measurement, movements. T4 is my tool. F750 is my feed speed. M0, M5, and M6 have to deal with motor spindle on, misting on, and I think this last one in Gerbil is let me see, the mister and the flood. Alright, so this is just on the mock-up screen, and I kind of figured that, right, this is what I want to put over here. I could change this layout dynamically as, depending on what kind of mode I'm in. This display over here, I'm not going to show you the refreshes over here because it's a little more complicated, but I can get the numbers to be this big. Alright, and at this size, I can display X, Y, and Z at this size. So this is just showing you some text down here, and then I can update this thing. But this is actually a touch screen. It's a resistive touch screen, so it's kind of a pain in the ass to press. But they do press down here, and by pressing these, this display actually will send me a message over the serial link that says what the new G code is. So it's possible to code up this really as a standalone device, and I can have buttons, and I can have text, and I can also do imagery, colors. I could change a lot of stuff about this. And in the development environment for this display, you actually design your graphical display, and then it kind of compiles it down to the binary that runs in the back of this processor, and all you could do is send over updates to this thing. So this is kind of showing you the refresh rate of the LCD that we're going to be able to get. So that's the project over here called LCD 2004. So I'll go ahead and close this workspace up, and I'll bring you up to the next one. Wheel Encoder is a simple project. Now the PSaw includes functionality for a quadrature decoder, so you bring in A and B. And if you've never used one of these little wheels before, on the back side you supply power to it, and then you have AB and AB complement coming out. And I just have this all connectorized up, and I plug it into the right connector down on the board. And then when I grab that, I have an interrupt routine that comes out on this line. Whenever I get a pulse through, I get an interrupt. The processor goes in and reads the current count value that's in here, and I just go ahead and stream that at the serial port. So I have a UART set up, and the UART, well, I can just show you over on this little board. So this little development, this whole kit here is $10. There's a breakaway development board over here. So this is like a debugger that does software debug. So that's a 2-pin device, 2-pin for software development, as opposed to JTAG, which requires 10. And also, when this is connected up like this, I have a serial link between these two, and then when you're actually running, when you say, I'm going to print out the UART, you can route that signal right into this, which gets put on the USB over here. So if I had this project running and we opened up a terminal, we could turn that knob and we could see the count coming out. It's relatively simple. If I were to show you the code for this, it would be, this is the entire code for this whole project. I do a serial start, which turns the UART on. I do a serial print string, which just lets me know that I'm running this project. I do a decoder start, which enables the decoder and the hardware decoder to get on. And then I do a count last, and I get the current count, right? And it turns out that that's going to be 0. And over here on the design phase of this, you can come over here, and it's really kind of cool. You can have 8, 16, or 32-bit counts, and this is kind of an absolute counter. So when it comes up, when you do a start, it zeroes that count out, and you can actually set the count as well as read it. So you can, like say you're doing a homing operation, and you want to set this encoder count, this decoder count to something having to deal with the absolute machine coordinates, or you can potentially, when you switch coordinate systems, you can swap this number out and have it be relative to the coordinate system that you're in. So you not only have the resolution of either plus or minus 127, but up to 32, which is, it's going to be plus or minus 2, what is that, 2 trillion. And this is another kind of cool thing, is that these encoders, if you've never worked with them, they'll send you a pulse train out from A and B, and depending on which one's high and which one's low, you can kind of determine which way it's being turned. And right now I'm on the 1x setting, which means that I get a pulse out every time I get a single step out. So if you look at this, you'll see that I'm getting a pulse when this one goes high. I get a pulse when this one goes high. I get a pulse when this one goes high. So what that means is that my knob is 100 detents per rotation. So every click is 1/100th of a turn. But I can change that. I can make it a 2x, which means that I'm going to get out a pulse on every transition of B. Okay, because this one goes high, I get one. This one goes low, I get another one. Or I can go 4x, where I get a pulse out on every transition of both sides. So you get that one, this one, this one, and this one, and then we start over again. So this is nice if you want more resolution out of your knob. But it turns out that this decoder, it doesn't do me any good on this jog wheel, because you can't position this jog wheel in between the detents. So it doesn't do you any good to count F2 or 4x. So I'm just doing 1x, and that's going to be fine because one turn around here is, you know, every click, it's 100 pulses per turn, which makes the math easy for the controller itself. So I'll go back to 1 here, and then down here in the let me see here in the, oh, I was checking the direction of this. Well, whatever. So I look and I get this decoder count, and actually this one is the polling version. Doesn't even use interrupts. But anyway, so this one just says if the count's different, go ahead and print the new and old count. All right, we'll close this project up. We'll move on to the next one. Next one is going to be feed override. It's just an let me get that pot out. So I have these little pots that I got over at All Electronics, and what's kind of nice about these is this is an analog potentiometer. So we have our normal, you know, 3 pins up here. This blue thing here is the potentiometer part, and it's a 100K pot. But the knob motion actually has about 30 detents in it. So when you turn this, let me just come over here. If you can hear this, I don't know if you can hear this or not, but it does click and stop. And this thing actually has 2 additional switches on it. So when you get all the way down to the counterclockwise position, you can turn it, and you can turn it off. So this is another switch over here at the end, and then this button, you can press this. Okay, so it has 2 switches back here on the back, and I have all that wired in to a connector over here, and I got these, I don't know how many they got of these over there, but I got to end up getting about 5 of these, and they're only like $1.50 or something. This is really a wild pot that I've never seen one that's kind of this complicated. But if you look at the project for this, what I end up doing is I bring in, let me just make this a little bit bigger here. Yeah, there it is. It's out by 2 pins. These are the 2 switch positions here coming in, and I just have them defined, something or other. And I'll get an interrupt whenever either of these 2 change. And the PSoC, like most microcontrollers, will enable you to do pull-ups on the individual input pins. So I don't actually need resistors on those. And then I'm reading the feed override into a A to D converter, and I take those values whenever anything kind of really changes, and I pump it out of UART. And so I don't need to show you that over here because I don't. Yeah, we're just going to blow that off. I mean, it just is a display. It tells you on and off for both switches and what the pot value is. And I'm running my potentiometer from 0 to 5, so I have this A to D configured so that it goes from the VSS-A, which is the analog ground, up to VDD-A, which is the plus 5 on my particular board. And it's a free running A to D, so I don't need any. I'm not going to do any interrupts. I just read the value out whenever I come around. And I can set the resolution of this from 8, 10, and 12. And by changing this resolution, you get a little less resolution, but you can increase your samples per second. So you can kind of see over here that, you know, even at 12 bits, I'm able to do 100 kilosamples per second, which is kind of a lot. All right, so I'm not going to show you that project running. I'm going to move on to the next one. The next one is, that was feed override. We went over wheel decoder. The next one is this MCP2307. All right, so this one is interesting as well. This one's, you know, pretty dang impressive actually. So on our top design, we have a driver over here, which is an I2C driver. Goes on the schematic. These switches and LEDs are driven by these two I2C devices, which are, you know, port expanders. I talked about that a little bit. And so with one I2C controller, I can just pump out commands and actually change those. And the other thing that's kind of nice about this, if you were to read about this part has interrupt outs, and so you can individually control. If these are inputs, you can set up an interrupt structure inside the part that says if it goes high or if it goes low or if there's any change on the configured pins. So there's a bit mask in here, and if either of those go high, low, or change at all, send me an interrupt. And then you can so you have interrupt A does the A bits, and interrupt B does B bits. But internally in the configuration register, you can also order these together so that you can run one interrupt line back over to the microprocessor for any of these pins. And these interrupt pins themselves default to being open drain or open collector effectively. So you can run multiple versions of these things on a single interrupt line. And that's what I'm doing here, and then I also have the ability to reset this device. If for some reason it gets kind of screwed up for some reason, I can reset it. I can get a nice clean reset and then send the configuration over to both of them. And then I'll get an interrupt basically coming out of the chip whenever any of my buttons are pressed. So over on the hardware design, I have this I/O pin here connected up to my board, and whenever any of those input pins are toggle, I get an interrupt over here, and I read in both the switches, and I do things like that. I update my LEDs based on the interrupt that actually happened. I have a serial transmit line, so it kind of does tell me what buttons I'm pressing and that type of thing. And down here I have a 1 Hertz clock running my LED on the board, which on the PSaw board it's at a specific location, and then I have I/O reset. So I have all these things in here. So this is the code for that, and I'm going to go ahead and program this in here. We haven't done this in a while. So I'm going to have to build this thing. I'll go ahead and show you this build process if I can figure out where that little thing is. So the build process comes through. Oops, it already flashed it. All right, well that's not good. Let's do a build and clean so you can kind of see what this thing actually does. So I'm going to do that. I just did the clean. And then this little button over here is program, which actually will go through and build the application. So on the PSaw side, they consider the application the entire device. So the hardware design, which includes the digital fabric as well as the analog fabric. And it goes through and you can kind of see what it's actually doing. These devices are, you know, if you've done any FPGA work, you kind of get the gist of what it's doing. It's doing all the placement and optimization from a hardware perspective, and for both digital and analog. And now I'm compiling my Cortex M3 code using GCC, and I pull it over, and now I've programmed my device, so now I'm done. And we see over here on my blinking light is blinking at 1 hertz rate, and if I go in and change this clock frequency down here to something else, my LED will go a little slower. So I can, like, let's make that half a second. So it's no, well, I did that the wrong way. Well, that's just going to make it blink faster, right? So it's going to go through and do this again because I changed the hardware design. But, you know, it didn't take very long to do it. So this is going to blink. No, it's going to blink slower. Half a second is slower. All right, so let's see. Let's make sure. It's pretty late here. As you can see, it's just after midnight here. All right, so here's my LED blinking. It's blinking slower. Now it's at a kind of a, you know, half a second on, half a second off. All right, let's go see if I can turn this over and show you what this is doing on this side. And this is kind of the orientation. Let me unplug this other crap. Just yank this out. Get this out of here if I can. Man, those are tight. Well, it doesn't look like I'm going to be able to do that. All right, we're just going to live with it this way. All right, now let me bring my control panel back over again. So my control panel is sitting like this, remember, and these are my buttons on the side. There's my LCD screen, and then I got 3 indicator lights up here. So this thing is going to kind of fit through here. These things are going to fit through here, and then this whole thing attaches. And then this IR receiver is, I don't have a hole in this thing, but that hole is going to reside right around here. All right. And I'll try that out before I put it all together, and if it doesn't work, I'll just move this IR receiver. The IR receiver is a function of a different project on my GitHub page. It's kind of a baby step just for the IR receiver. But I'll go ahead and reset my board, and you will see my LED patterns change. So I'm going to press the reset button, and I do a little light show to show you that all the LEDs are working first. Let's see if I can do this. Of course I can't. Alright, so that just shows me that all the LEDs are on and off. And then now, what I have programmed in there is these 6 buttons up here are actually toggles. So if you press on one of these, it toggles both that one and this one. No, it doesn't toggle this one. This thing down here is counting in binary for every button push up here. Okay, so if you kind of concentrate on the bottom side, you'll see the binary pattern is going. And then up here, all these things are alternating. So why I'm doing this is I want to show you the brightness of these LEDs. These are ultra bright LEDs from Cree, and I'm running these at 10 milliamps. And if we come back over to the schematic, you can set the milliamp of there's current limiting resistors here in the design, and I'm just using straight 220s. And this is a 5-volt part. So 220 works out to be with the forward voltage across the diodes. This ends up being about 10 milliamps. And you can see that they're really bright, really well illuminated. I'm really pleased with the look of this. And we'll go from there. But I did mention in my future to do, I can put in those RGB LEDs, you know, that you see in these RGB LED strips, and that uses a WS2818 chip, so I can get an ultra bright surface mount package that will fit inside the hole on the back side of this. And I can light these up with red, green, and blue if I can get that to it's fairly easy to do that because those things are just using a well-known protocol. I didn't know what these parts were for a while, but then as I soldered this together, I found this one, which is a great find. I don't know if you can see this or not. This one actually had a part number on it as a sticker, so I found it. It's 82-350-12. And this is a, what the heck did I decide this was? Shoot, it is not a keystone part, not amphenol. Oh crap, what is it? Well, go over to my GitHub page. I think I have that over here. Under the data sheets. Oh, it's a gray hill. Okay, so it's this thing here. And Gray Hill still makes these. They're available, and you can buy them at DigiKey. They're fairly expensive. A 3-banger like this is about $5. No, in the United States, a 3-banger like this is about $9. That's without the illumination in the back. But I found that these are also available in this gray, as the surround is gray, and they're also available in black. I found a place in China that's got like, I don't know, 500,000 of these 3-bangers, and they're selling them for $5 a piece. All right, so that's that. Let's go back over to my PSaw thing here. Let's see if there's anything else I want to talk about. We'll close that up. And so my goal here is, I'm pretty much done with my demo side. My goal is, to complete my work B1010 with my controller over here on the left-hand side. I'm using a PSaw controller. I'm using every pin on that PSaw 5LP. I've got a schematic here. And here's my board layout. Here's what the board's going to be rendered looking like. And I don't have pictures of the board. If you didn't watch last video, this whole thing is called my Hyatt controller. Dale Hyatt was one of the original cabinet makers for Fender back in the very early days of Fender instruments. So I think what I got to tell you is, like all designs I've ever done in the past, is this is version 1.0. Now keep in mind these boards cost me like $2 each. All right, I got 10 of them for $20. And as I started doing my baby step code, I realized that I kind of messed up in the fact that I want these 2 pins to be used for my serial debugging. And originally I had these laid out in such a way that I was using all these pins over here, and I had some spare CPU pins on this side that I kind of brought out onto this connector over here. So I kind of had to unallocate these 2 pins for software debugging, and then I had to kind of use up these other 2 extra pins over here for communication with over my radio link. So that's I'm already now at 1.1, right here, 1.1. Oh, the beauty of this is that my rearranging here will be a relatively easy fix on this board because it's only 2-layer. I cut the traces and just kind of patch in some blue wires and make the current board's 1.1 revision, and then I don't have to ever worry about revisions for the boards themselves. All right, well, that's I think that's it for today. Oh, let's talk about this little radio link right here. This week I've been working on another project. I use these little Wi-Fi boards here, these ESP8266 boards. These are Wemos D1 minis, and I'm able to get these. This is a complete Wi-Fi package that runs the Arduino libraries with a USB connector on the backside and a reset switch and an LED. I was able to get a bunch of these. I bought like 10 of them. I was able to get them for about $3.50 each. So I'm going to have this thing be Wi-Fi enabled. And I do a lot of different projects with these. So I have a template project on my GitHub page that I just can base a lot of my ESP designs on. And I'll do a quick show you that thing here. To come over to my GitHub page here. In repository, I have this thing called the ESP8266 Template. And this one is there's a lot of templates like this out there on GitHub. This one's mine, and I want to keep it as simple as possible. But it does have a ton of functionality. So there's a web server built into this. There is an HTTP update server, so I can do over-the-air updates to this chip. It's got a Wi-Fi manager in it, so what happens when you bring these up initially, they can't connect to an access point because they don't have the access point credentials. So it turns into an access point itself instead of being an AP client, and you can connect to this over your phone and set the credentials of your local network, and then it reboots, and then it connects to your existing infrastructure. It does this thing called, I think that's multicast DNS, which means you can give this a name, and then in the browser you can, see if I can hook this thing up. We'll just show you. In the browser you can use a specific name. You don't need to know its IP address because, you know, a lot of people are just using straight DHCP for allocation of their devices on their network. And I'm going to unplug this because I don't want anything to happen to either of my boards here. All right, let's see if this is going to work. Okay, so it got configured. It made it through its configuration, and when it's blinking in this pattern, let me get this out of the way. It's blinking in this pattern. That means we're connected to it. And if I connect it up over a serial link, I could see that it's actually streaming data over serial as well. It's going to be a little challenge. Let me see if I can do this real quick. All right, let's bring up my device manager and see what the serial port got allocated as. It looks like it's COM18. You're going, man, what is going on over here? Oh, great, I only have a COM18 on this side. All right, well, let's just see how fast I can get this going. We're doing a serial link. We're at COM18, and I'm at 115.200. We'll open that up. And I'll reset this guy here, and you can kind of see what comes out on the debug port here. So it prints out my template information, and it's telling you, okay, I got this out. This is my IP address. My web server got started at this IP address. My OTA updater, my MST, my multicast DNS got working. And here's our local address. It's called office.local. I've also got a WebSocket server started, and I'm running a TCP server that does it's a bridge between a TCP socket and the actual serial device on the ESP, and I'm running at port 23. So if I take this over here and I open up this link in a browser, my browser will go out and ask for whatever that address is, and hopefully this is going to work. All right, so this is my little demo code running. These individual devices up here, or devices, these elements on my web page are updated over WebSockets, and this is a demo that I got out from somewhere that's actually plotting some values of these ports. So I can show you the analog input because this has got a single analog input on this ESP8266, and its pin is, where is that pin on this thing? I can't see that guy. Oh, it's over here. So if I touch the analog input pin, I'll get a little bit of noise on it. Let me touch it with better connection. So I'm introducing a little bit of noise. I kind of lick my finger now, I'm touching the analog input pin. So you can kind of see the analog is changing. And I think the refresh rate on this query over here is about, I don't know, it's about a second. That's all controllable. So do WebSockets, blinks the LED without doing any waits, and that's configured. I'll show you this config.json file in a minute. It has a SPI file system, flash file system on it. It does JSON decoding using the Arduino JSON library. It pulls its configuration out of a JSON file on the flash file system. The index file that is actually getting rendered over here is index.html, which is actually on the flash file system. And so that's the thing that loads up these graphs and actually opens a WebSocket connection and brings that up here. If I'm boring you to death, I'm almost done. So I have an optional to compile a TCP to serial port bridge, which means that if you open up port 23 TCP socket, everything you send over that comes out the serial port. All right, so I'll show you the flash file system, which is actually really cool. So you got this specific URL called edit, and this is showing you the files that are actually stored on the internal flash part on here. They are stored as files, and you can upload new files to this thing as well as update the existing files, because there's an editor on here as well. So here's my index file right here, and it allows this index file actually uses this thing called, this old school way of, actually the first way of querying data from a backend without doing page refreshes, is HTML HTTP request. This came out a long time ago, and this is the way that originally the way Gmail actually worked. And I don't know if I'm probably boring you to death, but this example file on a template allows you to do HTTP requests, because it uses this is all running in the browser now because it's JavaScript. It also supports WebSockets, so this gets a WebSocket going, and it will the device itself has a timeout where it sends out a WebSocket information, and then this chunk of code here actually updates the entries. No, it's not showing up over there. It updates these entries over here, so you can kind of see that the Arduino uptime in millis is being displayed over here. I can also set the timeout value. I can come in here and say heartbeat. We change the value of the heartbeat interval. So right now it's set at 1,000, which is every second it sends out an update. But I'm going to change it to 10 times a second. And it says that the heartbeat got set. So if I come back over here, you can kind of see that now these numbers are updating much faster. And then down here, you can kind of see that my LED is running at the heartbeat rate, so it's blinking a lot faster. So this is 10 times a second updates, and I can kind of change that to a little bit faster even. I can make it 10 milliseconds, which is, well, that's this 10 times a second. This will be 100 times a second. And my LED is actually blinking. I don't know if you can see that. Well, I can't see it. You can't really see things above about 30 hertz, but we're running at 100 hertz here. So if you come over here, you can kind of see that this thing is really updating it fast. So the whole point of this is that in this design, I am going to be able to connect to my Gerbil board with a straight browser and actually be able to see the status of my Gerbil board. I will also be able to control it from a touchpad or whatever, but this adds a tremendous amount of additional functionality. Now I do have 10 of these boards made, And this is so darn flexible that I'm going to use this for a lot of other projects as well. Well, I have no idea how long this is, but I do know that it's very long. So I'm going to wrap it up here today and just tell you thanks for watching. This is the Valve Studio.